Hurry. Root means square value of AC. In short, RMS value. RMS value of alternating current, or is also known as virtual value or effective value. All these three are same. Now, what is RMS value? It is defined as that value of steady current which, when allowed to flow through a resistance for a given time, produces same amount of heat energy as is done by the alternating current through the same resistance for the same time. So here we are taking the time duration. There is no specification, so see a specific time duration that it is half cycle or full cycle. No, you can take any time duration of the AC, no problem. Okay? So it is taken in terms of heat energy developed. Suppose if I consider a DC circuit, for example, DC circuit, there is a voltage V is connected and there is a resistance R. Through this a current I flows. This is a steady current or DC current, and this steady current, let us say DC, IDC, then this steady current, if I allow it to flow through the circuit for a time duration capital T. Let this be the time period of the AC. Let it be. Then the heat energy developed H will be equal to I dC square into R into T, I could say. I dC square R into T. This is based on what we call Joule's heating effect. Now, if I take the same resistance and the same time duration, and if I send a AC through it, for example, if I send an AC through the same resistance, so this is I, the instantaneous value of AC flowing through it, then here this will be Vm sine omega t you are connecting, and therefore the current I will also be varying according to this sine waveform. So for this instantaneous value of AC current flowing through, I take a time duration that is capital T. Then what is the heat energy developed in this resistance for the current I flowing? That is what we want to find. But as this current is changing instantaneously, you cannot take the whole time together and write it like that. No. For that, you have to split that time duration capital T into very small parts, dt seconds, and then find the heat produced in that dt seconds as the current I flows, and then you have to find the time duration, total heat energy for the total time duration t seconds. Okay. So let the small heat energy developed for the time duration dt seconds will be I square into R into dt, I could say. So this for the very small time duration, this current I almost remain the constant. r into dt, I could say. Therefore, the total heat energy developed x will be equal to integral dx, that will be equal to integral Im square sine square omega t into r into dt from 0 to capital T, because we are fixing the time duration as complete cycle of the AC. Now after this is only mathematical integration, yes. So doing that integration I get h is equal to Im square constant r into integral 0 to t sine square omega t dt equals take. So when I take sine square omega t dt, you cannot apply the identities of integration directly. Therefore, I convert this sine square into a squareless format, and we get, or I can write that sine square omega t as sine square omega t can be written as 1 minus cos 2 omega t whole by 2. 1 minus cos 2 omega t whole by 2 I can take. Then, if I substitute this over there and do the integration, I get h is equal to Im square r into integral 1 minus cos 2 omega t by 2 dt from 0 to t. Okay. Now, when I do the integration for this, I am doing the integration now. That is integral 1 minus cos 2 omega t by 2 dt will be equal to integral 1 by 2 dt minus integral cos 2 omega t by 2 dt. Means I can split that into 2. So that will be equal to half dt from 0 to t, 0 to t. Half dt, if I take, it will be half into dt will be t from 0 to capital T minus integral, okay, cos 2 omega t dt, I can take it as 1 by 2 into sine 2 omega t by 2 omega between limits 0 to t. Now this will be equal to, this is 0 to t when I apply capital T minus 0. So this will be t by 2, and here if I take omega as 2 pi by t and we substitute upper limit t over here, it becomes 4 pi, and 0 over here it becomes 0. That means this value, by putting the limits from 0 to t, I will be getting this will be equal to 0. So what I am getting is integral sine square omega t dt will be equal to, that is from 0 to capital T, integral sine square omega t dt will be equal to t by 2. Please remember this value, because many different places in the same chapter we are coming across this integration so that you can write that value directly as T by 2. Okay. So, what is the results we are coming to? So, after doing all these things, we are coming to I square into. So, the value of this integration is now come to be into T by 2 itself. So, this is equation number 2. Okay. Therefore, as you take that value, compare with the first equation, the equation 1 was I dc square into r into t. This is the first equation, and as per definition, this and this are to be the same. That means I dc square r into t will be equal to I m square r into t by 2 it is. So r, t and t goes, and therefore I dc square is equal to I m square by 2, or I dc is equal to I m by root 2. And this IDC is what we call the RMS value of this IDC is equal to IRMS. Therefore IRMS will be equal to IM by root 2, or equal to 0.707 times I peak. Now this is the RMS value of alternating current, and the same way, with the same definition, instead of current you can take it as voltage and find the RMS value of voltage. VRMS is equal to Vm by root 2, or equal to 0.707 times Vm. And remember, this RMS value remain constant for the half cycle, positive half cycle, negative half cycle, or complete cycle of AC. So if you take any part of this AC and you calculate the RMS value, you will be getting the same thing only. So it can be treated as the constant value for what we call the AC supply. And you can see that for the transmission and the house supply, we are getting the value of our voltage around 230 volt AC. And this 230 volt will be remaining almost the same, and this 230 volt supply is actually the VRMS we are saying. And remember one more point, that is using AC measuring instruments. For example, AC voltmeter or AC ammeter. AC voltmeter or AC ammeter, if you are using it to find the voltage or current, that instrument measures only the RMS value. And this RMS value is the only measurable value of AC using the instrument. It's a very important fact to be noted. So if I say supply voltage of so and so in the problem, that supply voltage actually it is measuring or the mentioning of what RMS value. Got it? So it's very, very important. And one more point to be noted is that AC measuring instruments are constructed based on the heat energy developed by the alternating current or voltages. So based on heat energy it is measured, therefore the value changes as I square, right? So the division in the ammeter or voltmeter to measure AC won't be having the same spacings or equal spacing of the measuring scale. No, it's because of this there will be the scale will be of a different, what you call the scale marking won't be uniform throughout. Alright, so these are the points to be noted for the alternating current. So altogether we studied 4 different values for AC. 1, instantaneous value. 2, peak value. 3, average value. And the 4th one, RMS value. So when you go for solving problems and all, you must identify which value is actually mentioned in the problem, and accordingly you are supposed to take the values and do the calculations. Alright.